Yeah, good morning. We will start soon. So just wait for a while.
Yeah, good morning, sir.
Yeah, Swami sir, please continue.
Yes, sir, yes, sir. Sir,
Yeah.
shall I start or should I wait?
Yeah. Start, sir. Start.
Okay, sir, okay. Yeah, good morning, all. Now, today we are going to discuss about the third unit, which is dynamic programming.
Mix and both language, Telugu, English
Yes, sir,
mix.
yes, sir.
Okay. Thank you. Yeah. Go ahead, sir.
Okay, sir, okay. I'll start. So, dynamic programming, which is about, according to your syllabus, it is third unit. Just let me know, anybody can let me say once it is clear. Am I audible?
Clear. Everything
Yes,
is
sir.
clear.
Yes, sir.
Yeah, all right.
Yeah, which is dynamic programming according to your syllabus. It is third unit, where in the first unit we already discussed about algorithm characteristics and performance of an algorithm by measuring space and time complexities, and also that different asymptotic notations. Later, we have in the second unit divide and conquer approach and greedy approach methods. I will discuss later. Then it is dynamic programming. This is one of the approach to find an optimal solution. Where usually optimal means it is not minimum always. Optimum solution, maybe it is a minimum value to find, or it may be to find maximum value. So that depends upon the problem. For example, if it is a cost factor, then always it is minimum cost. If it is distance factor, it is always minimum cost. Whereas minimum distance. Whereas if it is in terms of with respect to the profit, the profit always were try to get a maximum profit. Then in that case, it is a maximum. So that is also an optimization. Optimization means always it is not a minimum. I want to say it is not always minimum. Minimum or maximum depends upon the problem. Where this dynamic programming usually it is usable for solving optimal solutions, but that optimal solution will get it by finding the sequence of solutions. So first year, what we are doing that if the problem is given that problem can be solved by using dynamic programming, the first step we are break down the problem, or we can say break down that complex problem into simple subproblems. And later, for each subproblem, we'll find an optimal solution. Once let assume that let me share once. Yeah. So this is in a problem which is complex. If you are thinking that this is a complex problem, this problem can be divided as P1 and P2 at two subproblems. So then I can say P1 and P2 are the subproblems. It can be solved. That is solution of this problem P1 individually, solution of the problem P2 individually. And this result will be stored, and this result will be also be stored. So this storing of the subproblems values is called memorization problems. So once the result will be stored, then if you want to use, this problem P1 in future reference, again, there is no need of solving this P1 again. Whatever the solution we are obtained here, that will be stored already here. This result will be directly we make use of that purpose. That is, once will be solved each subproblem solution and will be stored in somewhere else. That is memorization. So from that we can use in further references. So finally, we'll calculate all the result of these subproblems as a one single solution. So this is the main aim of the dynamic programming. But here, dynamic programming can be having the following two properties based on it is working on two properties. So just a minute. So one is overlapping subproblems, and optimal substructure. Based on these two properties, the dynamic programming will be working. Optimal substructure. So let me know what is this overlapping and optimal structure. For example, in general, if it is 1 plus 1 you want to calculate, what we have to do, we'll calculate 1 plus 1 will give a result 2. In the next, if you want to calculate 1 plus 1 plus 1, then what we have to do, we'll calculate 1 plus 1 plus 1, that is 3. Again, if you want to calculate 1 plus 1 plus 1 plus 1, then what we have to do, 1 plus 1 2, 2 plus 1 3, 3 plus 1 4 will give values. Just so this is the way we need to calculate. So what happens in the first step, if you want to calculate 1 plus 1, which is already calculated, the result will be stored in 2. Result we are saying that it is 2. Next, if it is summation of 3 ones, again we are calculating 1 plus 1 plus 1. If it is 4, 1 plus 1 plus 1, we are calculating. As it is, if it is a dynamic approach we are following. See, here if the value we want to calculate 1 plus 1, we are calculating 1 plus 1 and it is 2. In the next step, if we want to calculate 1 plus 1 plus 1, so it is not calculating again this 1 plus 1, 1 plus 1. So whatever it is in the previous step, just a minute. Yes, if it is a dynamic approach, you want to calculate the summation value. Then in the first case, if it is 1 plus 1 will calculate it and result will be stored in somewhere else. Then if in the second step, if you want to calculate summation of the 3 ones, these first 2 ones value will be stored already that is 2, and this 2 will be added with this last one, then we can say it is 3. If you want to calculate 1 plus 1 plus 1 again, now these 3 values which is already stored, no, that will be make use of these 3. Now we are doing only one addition, this 3 plus 1, then we can say it is a 4. See here, see here this value 4, summation of 4 ones. Here we are adding first addition, second addition, third addition. 3 additions we are doing here. 1 plus 1 plus 1. So whereas here for summation of in the using dynamic approach, the 3 which is already summation will be stored in the somewhere else. We will use that result with only summation, only single summation, single operation value. We get a value 4. This number of operations is reduced here. Number of operation it is reduced. So instead of this is a comparison of normal approach and dynamic approach. So this is a way it is dynamic approach we are calculating optimal solution. And if it is reduced, then from this I can say time consumption for calculating or solving a problem will be reduced. Then time complexity will be very less. But with respect to time complexity, it is okay. But as each time we are storing the value in some location, then it occupies some space, memory location. So with respect to, even though it is a space complexity is more, but time will be reduced. This is a general introduction about the dynamic approach. And we also, in the dynamic approach, I told you it is finding for the problems of optimal solution. So in the finding an optimal solution in dynamic problem, it is the problems which are solved by using recursive formula. Though it is not using recursive procedure or recursive programming, but here we are using the formula which is recursive. We want to use recursion, but mostly we use iteration only. So dynamic programming follow principle of optimality, we can say. Principle of optimality. So what principle of optimality says that the problem which can be solved by taking sequence of decisions. The principle of optimality says that the problem can be solved by taking sequence of decisions. So sequence of decisions in sense. So here in the previous comparison, in the first case, 1 plus 1 it is calculated and summation will be stored in the 2, the memory location. In the next step, summation of 3 ones, that first 2 ones which is already calculated, that sequence will be used, then addition with the single one. Next in the 4 ones, the 3 ones will be already calculated. So sequence of decisions we can say. In the sequence of decisions, we'll find one solution is an optimal solution. One is a final solution for the given problem. So in the dynamic programming, every stage we can take a decision. So see in the sequence of solutions, in every stage by stage, we are solving the solution for the given problem. And each stage we are taking a decision. So for example, Fibonacci series, we'll take an example, Fibonacci series function usually we'll write Fibonacci of n is equals to 0 when if n value is 0. In Fibonacci series of Fibonacci of n is equals to 1 if n value is 1. And if it is n greater than 1, that is if n greater than 1. So Fibonacci of 2, 3, 4 and so on. Then there is a formula Fibonacci of n minus 1 plus Fib of n minus 2 usually we follow as we know. Right? So for this, we'll trace one example. For example, here we'll do we'll solve one Fibonacci of 5. We want to calculate Fibonacci of 5. So usually the code for the Fibonacci will write int. Here I want to know, I want to conclude that how dynamic programming is coming into the picture, how it is optimal solution, how it is easy as compared to the normal procedure. I want to say that. So here, for example, if n value less than 0, it will give an error because, and if n value is 0, then it returns, that is Fibonacci of n value, return 0. If n value is 1, the Fibonacci of 1 is 1 only, answer is 1. Otherwise, if it is not 1, that is, then we calculate Fibonacci of n minus 1 plus fib of n minus 2. This will be stored in some value. And now it returns this some value as a result. So this is usually we follow a code, right? So here, see how Fibonacci of 5 will be calculated. So I told you that in the dynamic approach, the complex problem can be divided into sub-problems. So here Fibonacci of 4 can be categorized or divided into Fibonacci of 4, Fibonacci of 3. How it is? Based on this n value is, which is greater than, n value is greater than 1. When it is greater than 1, Fibonacci of n minus 1, 5 minus 1, 4, plus Fibonacci of n minus 2. 5 minus 2 is 3. These two summation will give the result here. But here also n still it is greater than, then it is again classified n minus 1 and n minus 2 is 4 minus 2, 2. Again 3 will be, again it is greater than 1. This is n minus 1, 3 minus 1, 2, and 3 minus 2 is 1. And this Fibonacci of 2 is also greater than 1. It is classified 1 and 2 minus 2 is 0. Where this fib of 1 direct value, it is 1. It is not required to further classification. As it is fib of 2, again it is divided fib of 1 and 0. This in the right hand side here, this fib of 2 and this is a fib of 1. This fib of 2 again classified fib of 1, again it is fib of 0 here. And see here, to calculate Fibonacci of value n is equals to 5, how many calculations, how many times we are calling fib function? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Total 15 times we are calling a function, right? So what we know, fib of 1 is value 1, fib of 0 is 0. The summation of 1 plus 0, it will return a function value to the fib of 2. Then fib of 2 is 1 plus 1, 1 plus 0 is 1. Now this is 1, fib of 1 value 1, 1 plus 1, it is a value is 2. And this is 1, this is 0, 1 plus 0, it is 1, fib of 2. This fib of 3 plus fib of 2, that is 2 plus 1 is 3 value, right? Coming to the right hand side, this fib of 1, it is a 1 value, fib of 0 is 0. 1 plus 1, 1 plus 0 is 1, and fib of 1 is 1 already. This 1 plus 1, it is 2. This value, 3 plus 2 value is given to the return to the function value fib of 5. Right? So here, just you observe here, coming to the leftmost child is this fib of 1. Here fib of 1 will get, we know the value, fib of 0. And by using this fib of 2, it is calculated. Among total structure, how many times fib of 2 will be calculated? See here, this is a one time fib of 2. This is also here again you calculated, again we calculated. Even though we are calculated first time itself, but again we are calculated here. Again here calculated. So totally 3 times we calculated. With respect to the fib of 3, here we calculated. Yeah, again also it is calculated again. So fib of 2 and fib of 3 calculated more than once here. So I told you that here, this is memorization problem. Once we calculated a subproblem solution, we can store the value in somewhere else. And further references, we can use that value instead of calculating again. So here, if you come to this fib of 2 value here, it is okay. Next here, fib of 1, fib of 3, it is calculated. coming to this place. Again here, no need to calculate this fib of 2 by using these two functions, which is already there. So if it is not required to calculate this and this function calling is not required, this calling function is not required. And coming to this here, fib of 3, which is already calculated here, and no need to calculate again here. So no need to call this function again. If it is not calculated, this child of fib of 2 and fib of 1 is not required to call, and this is also not required to call. So then leftover callings, how many times we are calling here? See, this is 1, this is 2, and this is 3, this is 4, this is 5. This is 5 here, it is not required. This one is also not required, fib of 1 already is there. And this is 5, this is 6. 6 times we are calling a function as if you follow dynamic approach. As we don't know the dynamic approach, we need to call the same function multiple times. Where there is memorization technique is not aware as dynamic programming approach is not followed. So this is the optimal solution. This we can say it is optimal. The problem can be solved in optimal way. So this is the way we need to follow. But here we are following top-down approach. As it is, dynamic approach is a not top-down approach, but here we follow top-down approach. And also we are saying that it is a recursive approach we are following. So most of the cases, the dynamic approach is not recursive programming it is followed. It is followed iterative method. Whereas iterative method, the sample code will be like int fib of int n will declare one array a of some size, and a of 0, that is Fibonacci of series, and if it is fib of 0, 0, and a of 1 also 1, which is very different. Then if it is n value greater than value of 1, that is if n is equals to 2, that n instead of taking n, I equals to 2 I less than or equals to n, I plus plus. Then what we have to call? So we have to a of I minus 1, same fib of I minus 1 plus fib of I minus 2 will be stored in a of I value. So if it is I value is 2, that is 2 minus 1, 2 minus 2, and so on, then it returns value a of n. So this is the iterative approach we are following. For this iterative approach, we'll take one array. We'll take one array for the same 0, 1, 2, 1, 2, 3, 4, 5 index of an array. So as it is, here we are following bottom-up approach. For example, I want to calculate same here fib of 5. So just yeah. So here I want to calculate fib of 5. Fib of 5, if its value is 5, then a of 0, a of 1. First it is a of 0, a of bottom-up approach. So for fib I value, for example, fib of 0, a of 0, a of 1. 0 it is 0 value, 1 it is 1 value. Then if it is fib of 2, that is I becomes 2. If I becomes 2, then we are using a of I minus 1 plus a of minus 2. I minus 1, that is 0, and here 2 minus 1, 2 minus 2. So this value, you know, already it is 0. This value, you know, it is already 0. By using this, where fib of 5 can be divided, as it is already there, fib of 5, we can use of this one, 0 value, 1 value. So in the same way, and if it is I is 3, I is 3 means I 3 minus 1, 3 minus 1, this value, and 3 minus 2, and it is 1 value. 3 minus 2 value is this one. It is calculated. if I is 4, that is if I is 4, then I minus 1, 4 minus 1, 3, and 4 minus 2, that is this one. This one, it will be used. If I is equals to 5, that is 5 minus 1, 4 value, 5 minus 2, this value. So this is a value we are calculating. Same, this is called a bottom-up approach. Bottom-up approach. So where here 0 plus 1, I value 2 means fib of 2. 0 plus 1, that is 1 value in the array. If I value 3, that is fib of 3. Fib of 3 is, we are using fib of 2 plus fib of 1. This 2 value, it is already 1. This is 1. 1 plus 1, it is 2. Now it is 2. Fib of 4, if it is, 4 will be used as fib of 3 and fib of 2. Fib of 3 value is 2 and fib of 2 value is 1. 2 plus 1, 3. So this is a value 3. Fib of 5, that is fib of 4 plus fib of 3. Fib of 4 value, which is 3, and this is 2. Total it is 5. Just let me. Yeah. So this is the way we will calculate it is following a bottom-up approach, I want to say. So bottom to top we are calculating bottom-up approach. So this is an introduction about the only the dynamic approach, how we are following. So how it will be reduced number of calculations as it is following the dynamic approach. The applications of dynamic approach, there are various applications of dynamic approach. The first one is multi-stage graph. This is the most important multi-stage graph. And the second one, all pairs shortest path problem. All pairs shortest path problem. And third one is 0 by 1 knapsack problem. And the fourth one is traveling salesperson. Traveling salesperson problem. So the various applications we have. Now we'll go with this multi-stage graph. As it is multi-stage graph. So in the multi-stage graph, we have a where it is a graph consists of a nodes and edges. And the nodes, each node is represented a circle. And each circle, that is nodes, is connected with an arrow called as an edge. Arrow upon a label called as a distance, or we can say it's a cost to move from one node to other node, we can say. So let's take one example here. Yeah. Take one example of multi-stage graph. Uh, just make a note of this graph, then we'll do. Just let me draw one graph. So there is a path from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and again 2 to 6, 2 to 7, 2 to 8, and 3 to 7, 3 to 6, 4 to 8, and 5 to 7, 5 to 8, 6 to 9, 6 to 10, 7 to 10, 7 to 9 also, and 8 to 10, 8 to 11, 11 to 12, 10 to 12, 9 to 12. And each edge as defined within a cast, or we can say distance. This is 9, this is 7, this is 3, this is 2, and this is 4, 2. Please note down the graph. So it is better for the reference for the future. And here it is the cost is defined with a red color. This we can say it is a red cost, or we can say distance also. Assume that so here this we can say it is a stage 1 or vertex 1. This 2, 3, 4 on the same line, stage 2. This is 6, 7, 8 and stage 3. 9, 10, 11 are the stage 4. And the last stage we have a node 12. Right. Our aim is to find out the multi-stage graph. That is optimum path from source to destination, which is sync. It is T. So source is 1 and destination is 2. Right. So this is a given graph. For this graph, we need to calculate distance, I can say, distance from source to destination. Distance from source to destination will be calculated as a tabular method. So in the tabular method, we have already used this tabular approach as it is a iterative approach. We are dynamic programming also Fibonacci of value calculated using iterative method by using this tabulation method. Before this tabulation method, we have used a memorization approach in the recursive. As it is already stored a value, this value which is already make use of that for the future references. Now it is by using tabular representation. So we are using the tabular representation to calculate a multi-stage graph. Each stage we have different types of nodes. So before going to discuss, here for example, there is a graph. See here, see one example. This is a graph, it is divided. So it is 2, it is 4, it is 10. It is 1, it is 1, it is 100, it is 50, it is 25. Right? Our aim is to travel from this source to this destination T node. So if we are not aware of this dynamic approach or multi-stage graph, whatever it is, so for once your location is at stage 1, that is initial node, this initial node, then there are exist 3 ways from this node to other nodes. Let me give node numbers 1, 2, 3, 4, 5. So you are at a node 1, you can travel from 1 to 5. Then there exist at node 1 3 possibilities. You can travel from 1 to 2, 1 to 3, 1 to 4. But we don't know which one is optimal. So by considering the the value which is given, that is distance factor, cost factor, we're taking the minimum cost route or minimum distance route. Where 1 to 2, it is defined as 2 units of distance or 2 kilometers or whatever it is. And 1 to 3, 4 units, 1 to 4, 10 units. Obviously, the minimum cost, which is 2 between the 1 to 2, we are selecting this is a one path in the first stage. Then we are moving from 1 to 2. Now we are at a second node. Second node, there is only one alternative path. There is no alternative path. There is only one way. So directly we can go for 2 to 5. 2 to 5. Then your destination is arrived with the total cost of 2. This is 100. 2 plus 100, 1 or 2 units of distance. And you are choosing this is a minimum path. But what happens that if you go with this path, for example, if you have chosen, actually there is a two more alternatives to reach a destination from 1 to 5. One is 1 to 3, 3 to 5 we can move, 1 to 4, 5 to 4 to 5 also we can move. 1 to 3 cost is defined as 4, 3 to 5 which is defined as 50, total 54 units. 1 to 4 it is 10 and 4 to 5 it is 25. This is 35. So as compared to this first path you have chosen, these two are the minimum. Among these two, third path 1 to 4, 4 to 5, that is via 4, which is minimum cost is 35. But we don't know the further distance from the next node, that is 4 to 5 or 3 to 5. So we have it initially positioned at node 1. So among these, there are three possibilities. Among the three possibilities, we have chosen 2. 2 is a minimum. So that's what we have chosen via 2 to reach the state 1 to 5. But which is not optimal. As we are not approaching any method, just we are used common sense to reach a destination from 1 to 5. So here we are not getting optimal solution. So because of this reason, then we have followed this dynamic approach way. And in the each stage, so here the name itself, multi-stage graph. Each stage we are calculating optimum path. Each stage we are calculating optimum path. That is you are following here. So consider this is a graph. And in this graph, there is a what stages 1, 2, 3, 4, and cost between that stages, cost 1. And this is D. I will tell you. As of now, you just assume that next stage. So there is stages vertices 1, 2, 3, 4 up to 12. 1, 2, 3, 4, 5, 6. Total 12 vertices, or we can say 12 edges. Right. Yeah. Now we are calculating, see here, cost of cost of 5 comma 12 we are calculating. What does it cost? The formula I'll tell you later. Just you follow this. Cost of 5 comma 12 means 5 it is represent a stage, and whereas 12 is a vertex or node we can say. So here in the graph it is a stage 5. In the stage 5 there is only one node 12. At stage 5 cost of 12. At stage 5 cost of 12. At stage 5 cost of 12 it is defined cost 12 to there is no further routes. 12 is the final state, so I can define it is 0. And calculate cost of at fourth stage. At fourth stage how many nodes are there? There are 3 nodes, 9, 10, 11. So cost of 4 comma 9 we need to calculate. Cost of fourth stage 10th node. Cost of fourth stage at 11th node. So cost of 4 comma 10, 9 means at cost at factor vertex 9 at a fourth stage. So it means that from 9 to always our destination is 12. In the reverse we are coming. We are following backward approach. 12. Actually our aim is to move from 1 to 12. Source to destination. But we are calculating cost factor in the reverse order. Why it is? Let you know. So it is 12 at the cost of stage 4, stage 5, cost of 12 node is 0. At stage 4, there are 3 nodes are there, 9, 10, 11. So cost of 4, 9 means 9 to destination 12. What is the cost? It is defined 4. So cost of 4, 10 means at stage 4, 10 to destination. Destination is 12. It is defined 2. Cost of 4, 11, 11 to 12, it is defined already as 5. Right? Just keep in your mind all these values. And here, this cost of 5, 12, 4, 9, 4, 10, 4, 11, which is already stored. I told you that memorization approach we are following the dynamic approach or dynamic method. So now we are calculating next stage, that is stage 5 over stage 4 over. Then we'll go with the stage 3. At stage 3, cost factor, cost of at stage 3, what are the nodes? The stage 3, 6 comma and 7 and 8. Right. These are the 3 nodes we have in the stage 3. So let me calculate cost of 3 comma 6. The cost of 3 comma 6 is nothing but at stage 3, consider a vertex. The vertex is 6. From 6 to 12, we ultimate goal is to 6 to 12, we have to move. 6 to 12. So to move from 6 to 12, what are the possible ways? There are 2 possible paths from 6 to 9, 6 to 10. So that is we can move from via 9th node and via 10th node. That is 6 to 9 to 12 is 6 to 10 to 12 is the 2 paths exist. Right. So actually in general, what we have to calculate, what is the cost of 6 to 9 and then cost of 9 to 12 and cost of 6 to 10, 9 to 12. So this is X, for example, this is Y. And among these X and Y, which is the minimum, we'll select that path. But again, we are calculating 9 to 2, where, which is calculated already. 4 comma 9 means 9 to 2. So here no need to calculate this 9 to 2 again. So we'll make use of this value, which is already pre-compiled. So cost of 3 comma 6 is defined. Just observe this is a formula. Minimum of C of 6 comma 9, that is a cost from 6 to 9 plus cost of at next stage 4 9. So actually what we have to write 6 to 9, 9 to 12. Instead of writing 9 to 12, I am writing this cost of 4th stage next node 9, comma, cost of one more approach 6 to 10 to 12. This is one more alternative. That is C of 6 to 10 plus cost of 10 is a node which is available in the next node, next stage. That is, we are at the stage 3. Now it is available at 4th stage, cost of that node. Then this we need to calculate. So that is just of the minimum of, there is a cost or distance defined from the graph 6 to 9. 6 to 9. This is the cost. 6 to 9 is 6 plus cost of 4 comma 9. It means that cost of 9 to 12 directly use this value, but we are not using this value. Why? Because I'll tell you just a minute. Yeah, and stage 2 I'll tell you. We are using this cost of 4 comma 9, which is already pre-compiled. So 4 comma 9 value is 4. That is 4 comma cost of C of 6 comma 10. So according to the graph 6 comma 10, there is a value is given 5. This is a value. And cost of 4 comma 10. Cost of 4 comma 10, which is already calculated as 2. Right, 2. Then that is a minimum value of 10 comma 7. That is a value 7. We'll take a minimum of these two. That is 7 is the minimum value. So how you got this 7? This will be is a final value at 7 considering second path. there are two paths, 6 to 9 to 12. Why are 9? Why are 10? So this is a value. The second value we are considering the minimum value. The second value is obtained from the path, second path. Second path we are considering the via the node is 10. Via the node is 10. So here we can say, so we are approaching from 6 to 10, 10 to 12, where is the, we'll select the final path. But where we have given this tabular representation, once we calculated here cost of this, cost of 5 comma 12, this cost of 5 comma 12 value is 0. That is, here just this is destination 12 to 12 only, and the cost is 0. This cost of 4 comma 9, stage 4 comma 9, stage 4 comma 9. At stage 4 comma 9, the cost is ninth. This is the node 9, no? The cost factor. What is the cost? Here in the cost row, we are substituting this value. That is 4. And what is the next destination? This is actually 9 to 12. Cost of 4 comma 9 means 9 to 12, I told you. This is 12. What is the next node? 9. Cost of 4 comma 10. That is 2. The next node here also 12. Cost of 4 comma 11. The value which is calculated 5. And next node from 11 to 12. Now here cost of 3 comma 6. Cost of 3 comma 6 means at node number 6. Node number 6. The value is 7. The value is 7. 7. What is the next node? Once you are at the 6th node, what is the next node? We are calculating the second path, 6 to 10, 10 to 12 actually. So we are moving the next node as 10 is the minimum path. So that is here you write 10. That is your right E10. So that's what it is. What is D indicates that if it is currently at this node, that is assume that this is a 3, then 3 to what is the next node we are to move, then what is the value of this cost value? So you're at node 6, where minimum cost value is 7, we are getting 7 value via this 10th node. So that's what we are the 6 to 10 we have to move. In the same way, just let me calculate 3 comma 7 also, this one, 3 comma 7. Same formula we are applying. At node 7 also, there are two possibilities. 7 to 9 we can go, 7 to 10. So that's what again, minimum of C of 7 to 9 plus cost of next stage, 4th of 9, comma, C of 7 to 10 plus cost of that 10th stage is available at 4th one. This is a value we need to calculate. So then that is a minimum of cost between 7 to 9, which is already defined as 4. 4 plus cost of 4 comma 9. Cost of 4 comma 9, which is already calculated over here, 4. 4. Cost of 7 comma 10. 7 to 10, there is from the graph 3. Cost of 4 comma 10, it is 2. 4 comma 10, it is 2. So then 4 plus 4 and 3 plus 2. 8 plus 2, 5. 8 plus 5. 8 comma 5. So this is the minimum value. That is the value 5 will consider. This minimum value we are obtained via this path 10. So cost of 3 comma 7. Come to 7 here, cost is 5. What is the next stage? Again it is 10. So, sir, any faculty is there here? That's it. Let me know anything. Is it clear? If you are clear this cost of 3 comma 6 and 3 comma 7 and so on, then you can able to calculate remaining all. I'll calculate, but just let me know 3 comma 8 again. Anybody unmute and tell me. Is it okay? Let me know. Is it board is comfortable and writing is comfortable, audio is comfortable? Anybody? So then again, cost of 3 comma 8. At the third stage, we are going to calculate for the node 8. For the node 8, 8 to 12 is ultimate goal is to reach, but there are again it is uh, two possibilities. I can go from 8 to 10, 10 to 12. I can go 8 to 11, 11 to 12. Among these two, we need to calculate a minimum one. So here there is a cost between 8 to 9. We need to calculate with the adding of cost of ninth node, which is available at the next stage. And also comma cost of 8 next to via 10, sorry, 10 plus cost of next stage that node first. And this is that is minimum of C of 8 comma 9, which is from the graph. So C of 8 comma 9, I think it is 5. 8 comma 9, yeah, 5 and 6. It is 5 plus cost of 4 comma 9. 4 comma 9 is 4. Already we have. And C of 8 comma 10. C of 8 comma 10, which is 6, and 4 comma 10 is 5. Among these, this is 9 and this is 11. 9 will be the minimum. 5 plus. So cost of 4 comma 9. Cost of 4 comma 9, which is 3 comma 8. Sorry. Cost of 3 comma 8 means there are two paths exist, 8 to 10, 8 to 11, not 9. So this is C of 8 to 10 plus cost of next stage, fourth stage of that node, C of 8 to 11 plus cost of next stage to that node, 11. So here minimum 8 to 10, cost of 8 to 10 is 5 plus cost of 4 to 10 is 2. Cost of 410, comma, cost of 8 comma 11. 8 comma 11 is 6 plus 4 comma 5. That is cost of 4 comma 11. This 4 comma 11 value is 5. So 7 comma 11, the 7 is the minimum. This 7 will be is the first parameter. First parameter, that is via this 10th node. So cost of 3 comma 8, minimum cost is 7 via this 10th node. So now third stage, we have completed the calculation part. That is third stage, 6 comma 7 comma 8 over. Then come to the second stage. The second stage nodes are 2, 3, 4, 5. Here I'll tell you why it is cost of 4 comma 9. So cost of second stage, second node we are calculating. So usually from the graph, what we have to do that at node 2 here, we are at node 2, ultimate goal is to reach the node 12. Then what are the possible ways? 2 to 6, 6 to 9, 9 to 12. Then we can summate the values 4 plus 6 plus 4. That is 14. Right. So here we'll write 2 to 12. 2 to 6, 9, 12. But here what I'm writing here according to the formula, minimum of C of 2 to 6, 6 to 9, 9 to 12 we have to do. But I'm writing cost between these two edges, 2 comma 6 plus cost of this 6 is a node available at next stage, where now we are at second stage. 6 is available at next stage, third stage, and the node number is 6. Cost of 3 comma 6. This cost of 3 comma 6 defined, and it reduces writing of C of 6 to 9, C of 9 to 12 again, which is already calculated. No need to calculate again this part.
So that's what here same 1 plus 1 plus 1 if you want to calculate. In the previous step itself it is calculated 1 plus 1 2. By make using of this result, now we have to do only one addition operation is enough to calculate three ones. In the same way again no need to calculate between this 6 to 9, 9 to 12. That is the memorizing. In memory, which is a value, already the cost of 3 comma 6 are already over. That's what it is. Cost of 3 comma 6 means 6 to 9, 9 to 12. But we are calculating 6 to 9 and 9 to 12, even though it is one step, we are make using of cost of fourth stage comma 9. So that is already defined as fourth stage of 9 comma 4 comma 9 is 4. So now cost of 3 comma 6, which is already defined, is already calculated as minimum value 7. So this is one path, 2 to 6, 6 to 9, 9 to 12. And not only one path, there exist three paths, 2 to 7, 7 to 10, 10 to 12. So comma C of 2 to 7 plus cost of next stage. This 7 is available at stage 3, comma that node. And not only 2 to 7, 2 to 8, 2 to 8 also, 8 to 10, 10 to 12. Then cost of 2 to 8 plus cost of 8 is available at third stage, that particular node. This is 3. Now, among these three, we will calculate a minimum value. So, cost of 2 comma 6 from the graph, 2 comma 6, which is 4, plus cost of 3 6, which is already calculated 7, comma, and cost of 2 to 7, which is in the given graph 2, plus 3 comma 7 value, just now we calculated here, 3 comma 7. 3 comma 7 is 5. Right, this 5 value. 3 comma 8 is 7. So 3 comma 7 is 5. Comma cost of 2 comma 8. 2 comma 8 from the given graph is only 1 plus cost of 3 comma 8 is 7. So in the minimum value, this is 4 plus 7, 11, 7 and 8. The minimum is 7. The minimum value is 7, that is 2 plus 5 from the second parameter. The second parameter here, the second parameter this one. From this we are obtained the minimum value. Means second path 2 to 7, 7 to 9, 9 to 7. So this is a path 7 to 10. This is the path minimum. That is when you are at a stage 2 at node 2, what is the next stage, next node 2? Via 2 we have to move. But we have a alternatives 2 to 7, we have one alternative, 2 to 8, 2 to 6 also, 2 to 6. So among these, this is the path we are getting the minimum value. That is next stage is 7. So cost of 2 comma 2 is defined in the table. Cost of 2 comma 2. 2, the cost is minimum value. What is the cost is here? 7. We are obtained 7 over. We are obtained over 7 here. Where then next node is, what is the next node? For the next node also 7. 2 to 7 we are approaching. 7 is the total cost, minimum total cost. This 7 is the from 2 to 6, 2 to 7, 2 to 8. Among that, 7 is the next node you have to move. Right? Then cost of 2 to over cost of we are calculating now cost of at second stage, not only node 3, we have 3, 4, 5. So cost of 2 comma 3 we need to calculate, cost of 2 comma 4 and cost of 2 comma. The same approach we are following is just identify cost of that means that from the node 3 we have to reach a final state to 12. Then what are the possible ways? From 3 to 6, 3 to 7, 3 to only two approaches. These are the two approaches. So 6 to 9, 9 to again from the 6 there are 12 via 6 to 9 or 6 to 10. Again from the 7 to alternative 6 to 9, 7 to 9, 7 to 10. So among these, this part is already calculated. Now you have to decide what is the next state only. From the 6, it is already over. That is 3 comma 6. It is decided. So from 3 at a node at a stage 2, from the node 3, from the node this 3, there are two possible ways: 3 to 6, 3 to 7. So among this, which is the minimum one? Not only 3 to 6 only. We are calculating entire 3 to 6, 6 to 10, 10 to 12, and 3 to 7, 7 to 12, 10 to 12. The cost of 3 comma 2 comma 3 means we are moving from 3 to 12. That is between 3 to the next stage. That is 3 to 6, the next node 3 to 6, plus that 6 is available at third stage. This is a stage of particular node, comma, and one more path 3 to 7 we can move, and cost of that 7 is available at a third stage. Only there are two alternatives. Then we are calculating minimum of cost between 3 to 6 from the graph. From the graph 3 to 6 it is defined as 2. From the graph 3 to 6, this one, it is as defined 2. And 3 to 7 it is defined 7. By make use of those, it is 2 plus cost of 3 comma 6. Cost of 3 comma 6 which is already calculated over here. Cost of 3 comma 6. So that is minimum value 7. So if you don't know this cost of 3 comma 6, what we have to know? Then again, this means 3 to 6 we have calculated. Then again 6 to, there are two paths, 6 to 9, 6 to 10, 9 to 12, 10 to 12. So here by considering this value, next we have to consider either this one or this one, either this one or this one. So again, instead of calculating again and again these values, we have calculated already at stage 3 of 6 node. So that's what it is directly we're using, which is already stored somewhere else 7, comma, between node 3 to 7 now. 3 to 7 from the graph, which is 7, and cost of 3 comma 7. Cost of 3 comma 7, which is already calculated as 5. So which is 7. This is 7 plus 5 as 12, 2 plus is 9. 9 is the minimum value. So 9 we are obtained from the first parameter. First parameter is this one. This is via node 6. So cost of 2 comma 3 value is minimum cost is 9. Via the next node is we have to go. So as it is exists 3 to 6, 3 to 7. So 3 to 6 is the minimum path we have chosen as with the cost of 9. Then in the table we are updating the cost of 3 comma 6. Here value is 9 and next node is 6. Then cost of 2 comma 4. Same here minimum of C of 2 to what are the possibilities? From the graph, there are three possibilities, 1, 2, 3. 2 to 6 we can move, 2 to 7, 2, 1, 2, 3 possibilities. So 2 to 6, 2 to 7, 2 to 8. Then 2 to 6 we are calculating plus cost of this node, comma 6 is available at which stage? Third stage. 6 is available at third stage. Just a minute. Cost of, sorry, cost of 2, 4 means at fourth stage, fourth node, second stage. fourth node, second stage, there is only one path, which is already over these three. Now this is only one path. So 4 to 8 only. So for that 4 to 8, yeah, minimum of, actually not minimum is not required, but follow according to that. C of from 4 to 8, it is only one path. 4 to 8 plus from 8 to 12, there are different paths. That is, node 8 is available at a third stage, 3, 8. Then it is C of 4 comma 8. 4 to 8 direct path, there is 11 plus cost of 3 comma 8. 3 comma 8, which is already calculated, the total value which is 7, then it is 18. There is no multiple options. So actually this min function is not required, only one path. No? So 18 will be updated 2 comma 4. First of 2 comma 4. First of 4. Cost of node 4. That is 18. And next node, obviously it is 8. Only one alternative, no other alternatives. Right. Then cost of 2 5. Cost of 2 5 is equals to minimum of, then 2 to, that is at stage 2 node 5. There are two alternatives, 5 to 7, 5 to 8. So then it is min function is required. Minimum of current node 5 to 7 plus cost of that 7 is available at next stage, that is third stage, comma C of current node 5 to 8, one more path, and that 8 is available at the next stage 3. So among this minimum and minimum value, 5 to 7 direct path, that is with the cost of 11, and cost of 3 comma 7, which is already calculated, the value is 5, comma cost of 5 to 8 from the graph, it is cost is 8, cost of 3 comma 8, cost of 3 comma 8 which is already calculated, the value is 7. So this is 16 and this is 15. The minimum is 15. 15 is obtained from the second path, that is 5 to 8 is the next path. So if you are at fifth node, next node you have to visit 8, where 7 also is there, but 8 is the minimum path. The cost is 15. So update the table. Update the table. Fifth node cost is 15, and the next node is 8. Next node is 8. So stage 2 over. Now at stage 1. This stage 2, 2, 2, 2, 3, 2, 4 over. Then stage 1 comma 1 you have to calculate. So in the 1 comma 1 there are possibilities 1, 2, 3, 4 possibilities. 1 to 2, 1 to 3, 1 to 4, 1 to 5. C cost of stage 1 to 1, that is minimum of C of, so from 1 to 2 is there, 1 to 3, 1 to 4, 1 to 5, right? 4 alternates. 1 to 2, cost between node 1 to 2, and cost at node 2 of stage 2, comma C of next part, that is 1 to 3, cost of 1 to 3 plus cost of that node 3 available at second stage, comma that is the third path, 1 to 4, cost of 1 comma 4 plus cost of that 4 is available at second stage, this comma, and next this is 1 to 5. C of 1 comma 5 plus cost of fifth node available at 2. Among these 1, 2, 3, 4 parameters, the minimum one you have to choose. Minimum 4 paths it is exist. So direct cost between 1 to 2 from the graph. That is, there is an arrow from 1 to 2. There is an arrow from 1 to 2. Cost is 9. 1 to 3, 7. 1 to 4, 3. 1 to 2, direct 2. These values will be used directly. 1 to 2, it is 9 plus cost of 2 comma 2. Cost of 2 comma 2, which is already 7 calculated. And C of 1 comma 3 from the graph. 1 to 3, the cost is 7 plus cost of 2 comma 3, which is already calculated, minimum value is 9. And this direct path 1 to 4. 1 to 4, it is 3 plus 2 to 4. 2 to 4, it is 18, only one alternative. And direct distance or cost from 1 to 5, which is 2 plus cost of 2 comma 5, which is already calculated as 15. Then here minimum value, this is 16, this is 16, this is 21, this is 17. So minimum we got here are two values as 16. This is also minimum, this is also minimum. The value we can take 16. If you consider this 16 value, then first path will be the best path. That is, you can move from 1 to 2, 1 after 2. And if you chosen this is a 16, that is second alternative, you can go with 1 after third node also. Where 1 to 2, 1 to 3 means here you can move 1 to 2 is the next one. Once you are at this stage, 9, 7, 3, 2, which is among first one. You can go 9 to 2 is one alternative. Then 2 to again it is further it is defined. Or otherwise 1 to 3 also you can go. That is the cost is 16. So there are two approaches it is followed. So assume that cost is just a minute. Here cost is 16. But what is the next destination? 2 or 3? 2 or 3. Right? So for this, first we'll define a formula as we did cost of 3 comma 7, 3 comma 8, cost of 1 comma 1, 2 comma 2, 2 comma 3. So we'll write a formula here. Cost of I comma j. I is called a stage, j is node or we can say vertex, is equals to minimum of C of this I, so j is a node, no? This node j to L. J to L means if it is cost of, if it is cost of 2 comma 2, for example, 2 comma 2 in the sense second stage, second node. There are three approaches, 1, 2, 3. 2 comma 2 is equals to 2 comma 6. What is 6? 6 is the next node available at next stage. That is J is the current node. J as it is. And 2 to it may be 6, 2 to maybe 7. L may be next nodes available from this node. 6, 7, 8 in this case. L, that is J comma L, plus cost of whatever it is L you consider. That is either 6 or 7 or 8. That L, which is available in the next stage. Now this is a stage at first stage. No, now these 2 comma 3 comma 4 available stage 2. If I consider 2 comma 2, second stage, second node, then second node is moving to the next node 6 available at third stage. That is currently you're at I, now you're at I plus 1. This is I plus 1. I plus 1 comma L. You consider, and this is a minimum cost formula. Actually, this formula as of now we are following. Cost of I comma j is equals to that jth node to the next level, that is next level node. What is the path exists from this this node to this node, and place cost of this node at particular level, cost of this node at particular level. That level, this definitely this level may available immediately to the next level of this I to I plus 1. So this is the formula it is defined, right? So basically, I told you that in the first case, itself, dynamic programming will works on sequence of decisions. But as of now, we are not considered any sequence of decisions as taken so far. Now we'll take decision based on the data availability. So this is the data availability. Based on this availability, we'll take decisions. Now you start from vertex 1 to, actually our aim is to move from 1 to 12 in this problem, right? So here we'll consider D of 1 comma 1. D of 1 comma 1 here same again. 1 is a stage. Second parameter again 1 is vertex, right? So 1 comma 1 in the sense 1 comma 1. What is the next path you are choosing from this table? If your current vertex is 1, what is the next path we are selecting? Here it is two options, either 2 or 3. Consider as a 2. Let consider 2. And means that currently you're at current node 1, you have to move if exist multiple paths, but you have to choose either go 2 or 3 as the next node. Yes, it is exist at node 1. 1 to 2, 1 to 3, 1 to 4, 1 to 5 exist. Among these 4 nodes, you can choose next node as 2 or 3. That is 2. 2 I have chosen. 3 also will select. If next stage, second stage, what is the next node you have chosen? 2. That is D of 2 comma 2. That is this one, second column from the table. If current node is 2, the next node you have, which is D, the column D, third column, second row, defined as a, you have to go seventh node as the next one. That is, first you go and next you have chosen 2. At a second, from the node 2, in the given graph, from the node to given graph, there are 3 alternatives, 2 to 6, 2 to 7, 2 to 8. Among these 3, it is defined 7th is the minimum. 2 to 7 you have to go. And next D of next stage, third stage. And that is the next node is 7. From 7 to which node it is selected? So go with the 7, node number 7. Node number 7 here in the table. Node number 7. What is the next it is defined? See here. The 7th node, which is defined as a 10. So here write 10 is the next node. And next you go with the 4th stage, which is the next node is 10. If it is a 10th is the 4th node, what is the next stage? So in the 10th, this is a 12, it is next. Yes, 12 is our destination. Then what does it mean? 1 to 2 you have to move, 1 to 2, and 2 to 7, 7 to 10, 10 to 12. If you follow this is the one path, then you'll get a minimum cost. So what is the cost from 1 to 2? From the table, or we can say here, otherwise your from the graph also. The node between 1 to 2, cost is defined as 9. And 2 to 7, cost defined is 2. 2 to 7. 7 to 10. 7 to 10 cost is defined as 3. From the graph, 7 to 10, C, 7 to 10, 7 to 10, 10 to 12, 2 to 7, 1 to 2, 9 plus 2 plus 3 plus 2. 9 plus 2 plus 3 plus 2. Total cost 16. 16 is the minimum cost. Right? Here two alternatives. Here I told you that if it is D of 1 comma 1, 1 comma 1, next path 2 I have chosen. You can also choose 3 also. This. Then what becomes here? At second stage, third node, where it is 2, now it is 3. 2 to 3. 2 to 3 means you have here 3 is the current node. Next node is, it is defined as a 6. And D of third stage, next stage of this node, sixth one, it is defined as again 10. D of next stage of next node is 10 is equals to 410. That is fourth stage, 10th node. 10th node number 10 here we have to see. That is 12 is the next. Then what is the next path? The next path it is defined as first it is 1, then it is 3, then it is 6, then it is 10, then it is 12. So 1, 2, 3 cast is 1, 2, 3 cast. 1, 2, 3 from the given graph is 7. 3 to 6. 3 to 6 it is given graph, it is 2. 6 to 10, 5. 10 to 12, 2. So 9 plus 7, 16. This is also 16. And if you follow this path also, if you follow this path or this path, you will get a minimum cost only. Two possible paths from the source 1 to 12. If you follow any of this path, we'll get a minimum cost. So here this multi-stage graph will, our aim is to calculate minimum distance from source to destination, and the cost of node 1 to other node will calculate it at each and every stage. Multi-stage graph, that's each and every stage we are calculating a graph. See, in the same example, if this is a graph, we are not following dynamic approach. Then initially we take position at this position, that is a node 1. Our aim is to reach this destination is D, 12. Then if there exist multiple paths from 1 to different nodes, that is 1 to 2, 1 to 3, 1 to 4, 1 to 5. Obviously, at this moment, we don't know further routes, but we know only these four alternatives. Among the four alternatives, definitely we'll choose, always you're in mind that with the minimum distance or with the minimum cost, we need to travel. So if I choose this path 1 to 2, the cost is 9. If I choose the path 9 to 1 to 3, 7. If I choose the path 1 to 4, cost is 3. If I choose the path 1 to 5, the cost is 2. Then obviously we'll select this path 1 to 5. Then again this 5 to, there are two alternatives 11 comma 8. We'll select this one again, minimum. Again from 8 to 10, 8 to 11 again. There is 5 comma 6, this minimum one we're selecting. Then 10 to 12, okay, this is 2 only. Then what is the total value here? 2 plus 8, 10, 10 plus 5, 15, 15 plus 2, 17. If you don't know and you are not approaching dynamic way, dynamic programming method or dynamic approach, then your cost is 17 and your path is 1 to 5, 5 to 8, 8 to 10, 10 to 12. But which is not true. There exists one more alternative with the cost is 16. There exist two alternatives with the cost, minimum cost is 16. If you are not aware of this dynamic programming approach and dynamic programming technique, then you may lose the minimum cost path. So that's what we have to follow multiple stages. We're calculating in each and every stage, we're calculating cost factor so that it is easy to find the minimum cost route from source to destination. This is about multi-stage graph. Right. Then second problem, and I'll just let me know, is it clear? I'll go with next second approach or second method, that is all pair shortest path problem. Shall I move to this all pair shortest path problem? Anybody? Anybody? Okay, I'll go with the next approach. Right. Second approach, all pair shortest path problem. All pair shortest path problem. So usually we have a one graph. So 1, 2, 3, for example. So all pair shortest path problem, a main aim of this all pair shortest problem is to find the shortest path between every pair of vertices, not from one to source to destination. So you will take one source, S1, then you can go with the S12, V2, V3, V4, and so on, Vn. Vn. So from one source to all the remaining vertices, all pair, each pair of this 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, and 1 to n. And 2 to 1, 2 to 3, 2 to 3, 2 to 4, and so on. This all pair name itself that will calculate a shortest path between the every pair of vertices. If this is a graph, then here we need to calculate from 1 to 2, what is the union cost, 1 to 3, what is it? Then with respect to 2, 2 to 1, 2 to 3. Then with respect to 3, 3 to 1, 3 to 2. So all pairs, for each and every pair, we need to calculate the cost factor. So sometimes it is not, if sometimes if it is of stage 1, there is a cost from 3 to 2, 3 to 2. According to this graph, the cost is 3. And as we are calculating for each pair of nodes, this cost may be reduced at least one, right? Then that we can say it is a minimum cost. If we are not calculating all pair of shortest path problem, we are not aware, then obviously we are calculating, we are considering the distance or cost between node 3 to 2, 3 only. There may be a chance to reduce. So how it will be reduced, I'll let you know. But the main aim of this all pair shortest problem is that we need to calculate shortest path only, but shortest path between every pair of nodes. Shortest path between every pair of nodes. So I'll select middle vertex 1. So for example, I'll check shortest path. How will shortest path will consider? So we'll consider other vertex in the middle vertex. We'll consider if you are calculating 2 to 3. If you are calculating 2 to 3, then there may be a chance to that there is no path between 2 to 3 directly. There may be a path 2 to 1, 1 to 3. This is called middle vertex. So 2 to 1 we are calculating cost, then followed by 1 to 3. So that is called a middle vertex. And I'll find out first whether the shortest path between all the pair of vertices going on this vertex or not. And first we'll say that 2 to 3. Next if it is 2 to 4. I can say it is 2 to 1, 1 to 4. I'm considering the middle vertex is 1. Right. It may be in the middle vertex is 3. That is 2 to 3, 2 to 4. There are two possibilities. So here you are assuming that you are introducing a middle vertex. This path, if you go with this way, there may be a chance to, just a minute. Right. So here 2 to 4 we need to calculate, but here we are introducing middle vertex as 1, middle vertex as 3. Means via, you may check if you go with via 1, the cost may be changing. If you go with via 3, the cost may be changing. If it is the cost is as 2 to 4, there is a direct rate with a cost of 7. If you go with via this one, it may be a 6, it may be a 5. If it is so, then you consider this updated value instead of going directly 2 to 4, you go with the 2 to 3, 3 to 4 via with the minimum cost is 5, you update it. So that is the way we need to calculate for finding the shortest path problem between all pair of vertices. So now we'll consider one example. Let me draw one graph. There are with the 4 nodes. One, two, three, and 2, 2, 1. And here also 1 to 4. 4 to 3, 3 to 4, 3 to 1 also. The cost is given. This is 2 to 8. 2 to 1 is 8, and 1 to 2 is 3, and 2 to 3 is 2, 3 to 1 is 5, 3 to 4 is 1, and 4 to 1 it is 2, 1 to 4 it is 7. Now for this we'll have one matrix. The matrix is A with 1 to 1, 3, 4. 1 to 1 the cost is not defined, so it is 0. 1 to 2 according to the graph, 1 to 2, 1 to 2, it is 3. 1 to 3, 1 to 3. There is no edge between node 1 to 3. If it is not, there is no edge exist, it is infinity. And 1 to 4, 1 to 4, it is 7. So self node 2 to 2, 3 to 3, 4 to 4, all are 0. 2 to 2, 3 to 3, 4 to 4 is 0. And 2 to 1, 2 to 1 which is 8, 2 to 3, 2 to 3, 2, and it is not defined. 3 to 1 is 5, 3 to 2 not defined, no exist. It is 1, it is 2, and 2 to 4 to 2 not defined, 4 to 3 also not defined. This is matrix with initially a power not, I'm saying, given matrix. Now, I want to calculate all pair of shortest path between all the pairs. Between all the pairs means, and each time I'll consider middle vertex as once it is 1, middle vertex is 2, middle vertex it is 3, and middle vertex is 4. So there are 4 nodes. Now calculate a power 1. As a power 0 is given matrix, now I have to calculate a power 1. To calculate a power 1 from a power 0 only. A power 0. So you consider a power 1 from the matrix a power 0 by placing first row a power 1, no? If it is a power 1, consider row of 1 and column of 1 from a naught. From a naught, first row, first column, keep as it is. Row 1, 0, 3, infinity 7. Column 1, 0, 8, 5, 2, as it is. And also diagonal values will be same. Diagonal values will be same. Then remaining values try to update by inserting, by considering middle vertex as 1. If it is a power 1, no, it means that we're considering a 1 is the middle vertex between the pair of nodes. If the pair of nodes is, for example, now we are calculating, now I want to know the value of this one, value of this. This we can say it is 2 to 3. Now I am introducing middle vertex, that is as 1, that is 2 to 1, 1 to 3. Is there any chance? Actually 2 to 3, which is 2 is the minimum cost. 2 is the minimum. It may be reduced, it may be chance to reduce, or it may be same value. So as it is 2 to 4 again, 2 to 4 it is not defined infinity, it may be updated. 2 to 4 means introduce a middle vertex 1 and 1 to 4. So we'll calculate a power this. Now we want to calculate The cost is 2 to 3, this one. To calculate this one, make use of previous matrix only, a power 0 only. A power 0 of 2 comma 3, a power 0 of 2 comma 3, it is not equals, right? So a power 2 to 3, we are introducing a middle vertex as 1. That is in a power 0 only, 2 to 1 plus in a power 0 only 1 to 3. There is a path between 2 to 3 by introducing a middle vertex 1. That is 2 to 1 and 1 to 3. Then it becomes 2 to 3 directly. Instead of direct path via this one. So cost of 2 comma 1 from the A naught, 2 comma 1, 8 plus 1 comma 3, 1 comma 3, infinity, right? Cost of 2 comma 3 from A naught, 2 comma 3, this is 2. So which is the minimum value here? So this value is greater than this existence value. This is existing value and this is a value obtained by introducing a new vertex 1 between the pair of nodes 2 comma 3 between. You are assuming that you may go via with 1, it cost may be reduced, but cost is not reducing as compared to the existing cost is 2 only. Now 8 plus infinity 8, this will become the update. If you go with the 1, 2 to 1, 1 to 3, the cost will be more. So no need to update whatever it is the previously. Now you write as it is that value only. This 2 only. Now try to find out this value. That value is a power of 2, 4. So this is calculating a1 power of 2, 1, but we are calculating 2 comma 4 from this previous matrix a power 0. So here also we are introducing 2 to 1. We are assuming that and we are saying that you go via vertex 1, that is 2 to 1, then 1 to 4, 2 to 1, 1 to 4. Introduce middle vertex as 1. Then a power 2 of 2, a power 0 of 2, 1, 8, and 1 comma 4, 1 comma 4 is 7. And 2 comma 4, 2 comma 4, which is defined as infinity. Though if it is introduced via, if you are moving via 1, the cost is 15, and previously it is cost is not defined, infinity cost. Then which is minimum value? Which is minimum value? We are getting a value 15 as minimum value. We are moving via this. If you are moving via this node 1. So instead of having infinity value, now you consider 15 value. 15 here. What does it mean 15? 15 means via this root vertex 1 introduced between these two pair of 2 comma 4 will cost is 15 as it is previously infinity. It is reduced. In the same way, calculate this is a value which is 3 comma 2, 3 comma 4. Then a power 3 comma 2 we are moving. So again, always we are in calculating a power 1. A power 1 means middle node is 1. That is 3 between 3 comma 2, 1. That is 3 to 1 and a power 0 of 1 to 2. So 3 comma 1, 3 comma 1 is 5. Plus 1 comma 2, 1 comma 2, 3. And 3 comma 2, 3 comma 2 infinity. And infinity is greater than always 8. So instead of writing this 3 comma 2 as infinity, your updated value is minimum. So when we should update this value? If this updated value is minimum, then this existence value. So in previously at this place, infinity, and now your updated value is compared to this value, this one. If it is new value is minimum, you update it. Otherwise, you keep as it is. Then a power 3 comma 4. That is a power of 3 comma 1. Always middle node is 1 only here. Because we are calculating, 1 comma 4. We are calculating a power 1. So from the value a of 3 comma 1, 5 plus 1 comma 4, 1 comma 4, 7. And 3 comma 4, 3 comma 4 is 1. So here this updated value only greater as compared to the existings. So 1 only here. Don't update this value. This is 12. This 12 we are not updating because the existing value only 1 is the minimum value as updated value. So 1 we should write. In the same way, a power now this value 4 comma 2. That is a power 4 comma 1 plus a power of sorry a power of 4 comma 2 is equals to not is equals to sorry just comparison a power 0 of 4 between 1 plus 1 to 2. So 4 comma 1 value 2 this value plus 1 comma 2 1 comma 2 value is 3 and 4 comma 2 4 comma 2 infinity. So infinity is always greater than this 5. You update it is 5. You update it is 5. And here a power 4 comma 3 again. Then a power 4 comma 1 plus 1 comma 3. A power 0 1 comma 3. So here 4 comma 1 is 2. We have 1 comma 3. 1 comma 3 is infinity. Right. So 4 comma 3. What is 4 comma 3 from the previous matrix? 4 comma 3 is also infinity. And 1 comma 3. 1 comma 3 it is 0. Sorry. It is 0. So just 1 comma 3. 1 comma 3. Not this one. This one it is infinity only. It is in. And 4 comma 3. 4 comma 3 also infinity. 1 comma 3 also infinity. So here infinity and 2 plus infinity. So here infinity and this is also infinity. Relation is equal. So don't update anything. Whatever it is the value previously, you keep as it is. That is in a power 1, right here infinity only. Now this is a updated matrix of a power 1. Check out this from a power 0 to a power 1. 0, 3, infinity 7. 0, 3, infinity 7. 0, 3, infinity 7. 802, second row, 802 infinity. 802, 15, which is updated. 5, third row, 5, infinity 0, 1. 5, 8. Instead of infinity, it is 8 is updated. So 2, infinity, infinity 0. 2, 5, infinity 0. Some values are updated. When it is updated via between those nodes, if you are following, you are moving via the node 1. Then by considering this a power 1, now you calculate a power 2. The a power 2 will be defined a power 2 will be considered to define a power 2, consider second row, second column values of the previous matrix will be same. Second row means this one 8, 0, 2, infinity. Second column 3, 0, 8, 5 as same. Diagonal values also same 0, 0, 0. Right. Now we calculate, go with the remaining values filling. That is, this value you have to complete this value, this one, this one, and this one we calculate. And in the order wise, but we are a power 2 we are calculating, but we are using a power 1 only. A power 1 of 1 comma 3. This is for this 1 comma 3, that is a power 1 of, what is the middle node here? A power 2 we are calculating, that middle node is 2, a power 1 of 2 to 3, a power 1 of 2 to 3, right? This a power 1 of 1 comma 2, consider this is a matrix, reference matrix is this one, 1 comma 2, 1 comma 2 which is defined as 3, and 2 comma 3 defined as 2, 1 comma 3 is infinity. So infinity is greater value, previous value is greater as compared to the current value. So update here as 5. Now a power 1 of 1 comma 4 via node 2, 1 comma 2 plus 2 comma 4. 2 comma 4. So 1 comma 2 as 3, 2 comma 4 15, and 1 comma 4 as 7. 7 will be the minimum value. So here 15. Don't consider this is 18. Here you consider keep as it is 7 only. Now calculate this one, that is 3 1. A power 1 of 3 1 via, sorry, a power 1 of via node 2. A power 1 of 3 comma 2 plus a power 1 of 2 comma 1. This a power 1 of 3 comma 1 is 5 value, 3 comma 2 is 8, and 2 comma 1 is 8. So this value will becomes a minimum. So keep 5 only as it is, as previously also 5. Now 3 comma 4. A1 of not A1 of 3 comma 4 via A1 of road vertex